Definite integral. Let us go back to the fundamental theorem of calculus. The fundamental theorem of calculus is the theorem. It is the statement that is connecting integration with differentiation. It's like integration is reverse engineering. You are reversing what differentiation does to a function. Suppose f of x is a continuous function on the interval ab, okay, closed interval ab, and suppose big F of x is the antiderivative. So this is what the fundamental theorem of calculus is telling us. The integral of f of x dx evaluated from a to b is equal to that. Okay, you will evaluate the antiderivative at the interval of integration. So it's going to be capital F of b minus f of a. So far, what we had been doing is we are getting the antiderivative. And the antiderivative is a function. But when you go to the definite integral, your final output is supposed to be a numerical value. Okay? It is a numerical value because you will evaluate the antiderivative f of b minus f of a. So these are the steps to do definite integral. First, you must get the antiderivative. Okay? Get the antiderivative, and you can just for the moment ignore the interval of integration because if you will always write the interval of integration, it will clutter your solution. And then you will evaluate the antiderivative in the bounds or interval of integration. It's going to be f of b or capital F of b minus f of a. Example, evaluate the integral of 2x minus 1 dx evaluated from 1 to 5. Okay, so that is how you read it. First, let us get the antiderivative. So the antiderivative using the linear property of the integral and your power rule, it's equal to x squared minus x plus c. That is the first step. Next, you will evaluate the antiderivative in the interval of integration, and this is how you write it. Okay? If you were to write this manually, you should write it in such a way that the bounds of integration is prominent. Okay? It should be a long bar, but I cannot find a long bar in the equation editor. Okay, x squared minus x evaluated from 1 to 5. That is how you interpret that symbol. X squared of 5 squared minus 5. And then minus 1 minus 1. Okay, you put that inside the parentheses. And so it's going to be 20. 25 minus 5 is 20, and this one is just equal to 0. Obtain the integral of sine of theta d theta evaluated from negative pi over 2 to pi. Again, we begin by getting the antiderivative. The integral of sine of theta d theta is negative cosine of theta plus c. And then we will evaluate negative cosine of theta in the interval of integration. Let us evaluate negative cosine of theta from negative pi over 2 to pi. So what you will do first is you will evaluate what is negative cosine of pi, and then minus negative cosine of negative pi over 2. Okay? So you will begin with negative cosine of pi. This is cosine of b. Okay? And then minus negative cosine of negative pi over 2. Okay? And so this becomes plus negative cosine of pi plus cosine of negative pi over 2. And negative cosine pi is 1 and cosine of negative pi over 2 is 0. Okay, so let us go back to how we evaluate trigonometric functions. I just have the feeling that you can no longer recall how this is done. Okay, so we begin from the unit circle in standard position. So the pi there, the pi, negative pi over 2, that's the arc length of a unit circle in standard position. So to evaluate negative cosine of pi, what you do is you trace pi, okay, an arc in the unit circle whose length is pi. One revolution is 2 pi. So half revolution and counterclockwise, that is pi. Okay, so how do you get cosine of pi? Well, what you do is the arc has an endpoint, and the endpoint has an x and y coordinate. It's a point in our rectangular coordinate system, so it has an x and y coordinate. The x coordinate is cosine of pi, and in this case, it's negative 1. But negative, okay, of negative 1 is just 1. Now, how about cosine of negative pi over 2? So negative pi over 2, you know how to interpret a negative angle. Okay? You will revolve the angle or you will trace an arc in the unit circle clockwise, whose length is pi over 2. The x coordinate of that point, okay, is cosine of negative pi over 2, and it is equal to 0. Get the integral of 3 times cosine of theta times sine square of theta, or the square of sine theta d theta, evaluated from 0 to pi over 2. First step is get the antiderivative. Okay? You can bring out 3 outside the interval sign. Now, how do you solve this? So I hope that your eyes now is keen to see that this one can be done by substitution. So let u be equal to sine of theta. du is cosine of theta d theta. Okay, so you will just replace this. Okay, so this whole thing, sine, the square of sine theta, that is just u squared. Okay, and this one, cosine theta d theta, that is du. Now look at that. Okay, from something that is kind of intimidating, it turns out that that is a simple function to integrate. So what is the antiderivative? You will apply your power rule. It is equal to 3 times u raised to 3 all over 3 plus c. 3 divided by 3 is 1, and so it's equal to the cube of u, or the cube of sine of theta plus c. Now that is just the first step. The second step is this. You will evaluate the antiderivative in the interval of integration. So this is going to be the cube of sine of pi over 2 minus the cube of sine of 0. So what is the cube of sine of pi over 2? Okay, sine of pi over 2 is 1. 1 cube is just 1. And sine of 0 is 0. So the cube of sine of 0 is also 0. So this is just 1 minus 0, which is equal to 1. Okay, so let us bring back our unit circle in the rectangular coordinate system, a unit circle in standard position. Okay, what am I doing here? Well, I am just refreshing our understanding of how to evaluate trigonometric functions, because you will do this again when we go to the polar coordinate system. We will do this often. So you will trace an arc whose length is pi over 2. That's 1/2 of pi, okay? And you will have an endpoint. That arc has an endpoint. The y-coordinate of that point is your sine of pi over 2. And in this case, it's 1. So sine of pi over 2 is 1. The cube of sine of pi over 2 is 1 cube, which is equal to 1. And then what is the cube of sine of 0? Well, what is 0? Okay. That is You are not tracing any arc length. Okay, so the initial point stays in the initial point. Okay, so the y coordinate of that point is 0. That is why the cube of sine of 0 is 0. So 1 minus 0 is 1. Now, how about this? The integral of dx over x plus 2 evaluated from 0 to 4. Anyone? Okay. Do you have an idea about how to begin? Again, you begin by getting the antiderivative. Okay? Well, this is how you can do it. Let u be equal to x plus 2. du is dx. It turns out that this rational function is just this, the integral of du over u, or the integral of 1 over u du. So this is one of those fundamental forms in integration. This is equal to ln of u plus c. Okay? And so it's equal to this, ln of x plus 2, the absolute value of x plus 2 plus c. That is the first step. The second step is to evaluate the antiderivative in the interval of integration. Okay? Ln of the absolute value of x plus 2 evaluated from 0 to 4. So ln of 6, okay? 4 plus 2 is 6. Minus ln of 0 plus 2. That's just ln of 2. Okay? You can already stop here. Ln of 6 minus ln of 2, because that is already a constant. That's already a real number. But just in case, I just wish to remind you of some properties of logarithms, because again, we will meet logarithms again. Ln of 6 minus ln of 2, this is the same as ln of 6 divided by 2, or ln of 3. So this one, ln of 3, is the value of this one. The integral of dx over x plus 2 from 0 to 4 is equal to ln of 3. I wish to go back to this function, 1 minus 1 over e to the x. You will see this in stat. You will see this in differential equations. And you will see this again even in psychology. Okay, we have this thing called the learning curve in psychology. And it turns out that learning curve, okay, looks somewhat like this. The curve defined by 1 minus 1 over e to the x. So let us get the integral of 1 minus 1 over e to the x dx from 0 to 1. Let us get the integral of 1 minus 1 over e to the x. What is the antiderivative? Using the linear property of the integral of 1 dx is just this. And it's equal to x. Okay? This one, the integral of 1 over e to the x dx, using laws of exponents, that is the integral of e to the negative x dx. What is the integral of e to the negative x dx? Okay, so let u be equal to negative x. du is negative dx, or dx is equal to negative du. This is the technique of substitution. So you must replace this by u and du. Okay? So dx is negative du. Okay, so that's like negative 1 du. So negative 1, I place it outside the integral sign. And you know that the integral of e to the u du is just e to the u. Finally, this is the integral of e to the negative x dx. It is equal to negative e raised to negative x plus c. So let us now put these things together, okay? The antiderivative of this function is this one, x plus e to the negative x. The next step now is to evaluate the antiderivative at the interval of integration. X plus e to the negative x evaluated from 0 to 1. Okay, that is how you read it. Let us evaluate the function when x is equal to 1. Okay, 1 plus e to the negative 1 and then minus the antiderivative evaluated at 0. So 0 plus e to the 0. Okay? E to the negative 0 is just e to the 0 and it's equal to 1. So this becomes 1 plus e to the negative 1 minus 1, and that is equal to e to the negative 1. And guess what? It's just equal to 1 over e. The integral of 1 minus 1 over e to the x dx evaluated from 0 to 1 turns out to be equal to something which looks really beautiful and simple. It's 1 over e.